So we'll continue the hyperpolarized summer seminar. This lecture will be focused on more on the MRI side. So we'll go a little bit over the RF hardware, so coils, and then focus mostly on different approaches to MR acquisition. Before we get into it, just curious with a show of hands, who's had kind of an MRI course before or is comfortable or familiar with different MRI sort of imaging approaches? So most people here are plugged in, so this will be good. So I'm going to kind of cover the whole range of this in about 60 or so minutes, so feel free to interrupt as we go. And these slides will be online later, kind of as a resource to follow up on if you have any questions in the future. So in previous seminars, we've gone over the physics of the DMP process, as well as the polarizer hardware, and Dave last week talked about compound development and some of the techniques there. So this week we'll focus on imaging approaches and coils for hyperpolarized carbon MRI. So if we think of this MRI traditionally, like in terms of what you'd call proton MRI, we typically have these trade-offs between spatial resolution, temporal resolution, and SNR. That is, you can typically have two of three. You can image at high resolution for a short amount of time, and you sacrifice SNR, or get high SNR and high resolution with long scan times. Right, so there are always typically trade-offs when you do any type of imaging study. Now, with DNP, it sort of turns this on its head, right? Because we have this huge increase in signal that lasts for a short amount of time. This idea of short scan times, they don't really hurt us in SNR anymore. And if anything, you want to image fast to try and minimize any sort of T1 related losses. So for the hyperpolarized case, shorter scan times actually lead to an improvement in SNR rather than the opposite that you typically have in proton. So the biggest trade-off that we have now with the DNP or hyperpolarized carbon is now between signal to noise and spatial resolution. And as we'll talk about how we use that signal over time to get the enzyme kinetics. So there are a few major pitfalls that I want to sort of just talk about or address briefly before we go into detail in a few slides. So the first is we have a limited imaging time or an imaging window with which to image this metabolism. These are around 30 or 60 seconds for species of 3T, so this can vary as a function of field strength and as a function of substrate polarize. We also have to deal with the reduced gamma or reduced gyromagnetic ratio. It's about fourfold lower for carbon than for proton, which impacts the gradient performance and some of our scan parameters. And we also have to introduce this idea or concept of RF decay. We no longer have T1 recovery that you conventionally have in proton or thermally polarized MRI. So this RF decay means we have non-recoverable magnetization, which means things like averaging or off because you don't recover your magnetization. RF calibration is more difficult and now of paramount importance, so you play the right tip angles. It also leads to case-based filtering in your images, which we'll talk about in a few slides. So let's first focus on the concept of T1 decay, right? So as opposed to T1 recovery, where you put your thermally polarized spins into a magnet and they recover, here they're going to decay. And so that means over time, your signal is a exponentially decaying function of T1. So the important thing here is that the shorter your T1 is, the faster your signal decays. So when we're choosing our hyperpolarized substrates, as Dave alluded to last week, we want to have compounds that have, or C13 sites that have T1 times as long as possible in order to maximize our polarization and maximize our imaging window, which is around, as a rule of thumb, 3 to 5 T1 times. And so there are, just to summarize here, there are four main pathways for relaxation. So your relaxation rate, or 1 over T1 that you observe. There are 4 main components, which are sort of dipole-dipole relaxation, scalar relaxation, spin rotation, and chemical shift anisotropy. And the relaxation rates of different sites are highly dependent on the local chemical environment. Having directly bound protons means you will relax via dipole-dipole and tend to have short T1 times. The more isolated carbons, like the carboxylic acids or quaternary carbons, tend to have longer T1 times, sort of as evidenced by site number 9 here, which has a 37-second T1 versus 2 and 6 and 3 and 5 that are on the order of 3 seconds. So for the carbons that don't have any attached protons, they typically relax via this chemical shift anisotropy pathway, which is proportional to the square of the main magnetic field, which is why when you go from 3T to 14T, for instance, the T1 of pyruvate decreases. So it's just something to keep in mind when you're doing these imaging studies and looking at different field strengths, that the relaxation rate will vary as a function of field. Now, on top of the sort of concept of T1 decay, we talked a little bit about this difference in gyromagnetic ratio between proton and carbon. And thinking back to some of the basic equations that we have in MRI, we know that our sort of slice thickness and our K-space trajectory are modulated or impacted by gamma, right? So for the exact same gradient waveform that we play out, we cover K-space differently between proton and carbon because of that 4-fold difference in your gyromagnetic ratio. So because we cover K-space differently, it's going to impact our slice thickness, it's going to impact our field of view, and it's going to impact our resolution. So because we have this 4-fold difference, how will it impact our resolution? So if we play this exact same waveform on proton and we have, let's say, a 1 millimeter thick slice, what will that corresponding slice be for carbon?
A fourth of a millimeter?
Oh, so you're saying it'll be thinner.
Yeah.
If you agree with Nick, raise your hand.
Or is it 16?
So how about this? Who thinks, the equation's there, who thinks the slice gets thinner? Or who thinks the slice gets thicker? Right, so which one? It gets thicker, right? How about for your, let's say, your effective spatial resolution? If we had 1 millimeter in plane for proton, would carbon be 4-fold thinner or finer, 4-fold coarser, 16-fold, let's go squared? Which one? I can wait all day.
Coarser?
It's coarser. Yeah. How much? 4-fold. Exactly, right? So you're sampling K-space more densely, right? Because you can see here, because we're sampling more densely, our field of view is increased. We're not going out as far in K-space, so resolution is worse, right? So all things being equal, you play the exact same slice select gradient, you play the exact same encoding waveforms or encoding gradients, you're going to have 4-fold thicker slices or larger FOV, which sort of means your field of view is brought back. And so, in other words, your gradients have to work 4 times harder for carbon than for proton. So if you have the extra gradient headroom, you can increase the gradient strength. If you are already at sort of Gmax or close to the gradient maximum, you then have to increase these durations to achieve the thickness or the resolution you want. So something to keep in mind, this will come up again when we talk about sort of spectroscopic imaging with EPSI and some of the trade-offs that this has there. So thinking about RF coils, something we sometimes take for granted, right? Because we're doing this sort of sort of structural and then functional or metabolic imaging, we need both proton and carbon coils. The proton primarily for localization or structural information, and the carbon coils for metabolism. Right, so on a clinical scanner, something we sometimes take for granted is because oftentimes that proton body coil is built in, so it might not have the best sort of filling factor or SNR, but it's more than adequate to get a localizer, some T2 weighted images, so we know where our carbon signal is coming from. But on preclinical systems like the Varian and the Bruker, there is no proton body coil built in. So that means we have to either purchase or design coils that are so-called dual tune that can acquire signal on both proton and carbon, or if you don't have that, you can swap between proton and carbon coils between your anatomic scans and your carbon scan. While that does work, it does introduce some potential for misregistration when you swap the coils out and move the inserts around. An extension here is that you can oftentimes use multi-channel arrays. This is more of a coil type you would use on a clinical system for clinical studies rather than on the preclinical ones, but kind of introduce it nonetheless. They offer a number of benefits over a single channel birdcage or volume coil. You have typically improved coverage and improved sensitivity compared to a single channel birdcage. So here is a SNR comparison that Adam did between a single channel volume coil and then an 8-channel and 32-channel receive coils. And so while you have similar SNR at the center, farthest from the receive array, you definitely have signal enhancement as you get closer to those smaller elements. It also enables undersampling via parallel imaging that you can't do with the single element coil. One thing to note here is that it is important to think about how you combine this multi-channel data. Not a problem for the preclinical single channel systems, but when you have multi-channel data, combining it in an SNR optimal way is important, because while sum of squares combination is simple and routine, it does lead to non-zero Gaussian noise and this Ricean bias-like noise, which can impact quantification. And so there are many approaches to combine this data. Your SVD or eSpirit, what we call RefPeak, where you estimate the weights based off the pyruvate signal. I'm just going to introduce them here and say there are lots of ways to do it. Any of them are better than doing a simple sum of squares. If you ever find yourself working with multi-channel arrays, the code for all these techniques are available on Peter's GitHub. The paper is here to go through the different details. But long story short, as you go to lower SNRs, so either for late phase dynamics or for metabolites that have just lower SNR like bicarb due to lower perfusion and lower conversion rates, you're going to be in a lower SNR regime. So when you're trying to quantify that, let's say via a metabolite to pyruvate ratio, as you get to low SNRs, that non-zero mean leads to bias in your ratio. And if we look at individual images here, we can see that it does a much better job at, I want to say denoising, but it optimally combining the multi-channel data than a simple sum of squares, which has the channels weighted equally. So now that we have our coils, we need to get our, yeah.
Is this, let's say, the comparison, does it also affect how many elements you have in the coil? So one algorithm, maybe it's better, let's say if you have 16, but the other maybe it's better for the 32, or
between sort of the
different
eSpirit.
Yeah.
So I found that for those, they all perform pretty well. As you have more and more elements, I think you see more and more of a difference between the sum of squares and the data-driven approaches. We did simulations with an 8-channel coil. Then we had actual data from a 16-channel array for the abdominal imaging and a 32-channel array for head imaging. And there, typically we just default to using the RefPeak method because there are no user tunable inputs. It's basically estimating the coil weights or sensitivities from the pyruvate data itself. Whereas these spirits, you have to set different eigenvalue thresholds, and with the SVD approach, it's not readily applicable to imaging-based approaches. So getting down in the weeds, there might be some differences when you have fewer elements, but I wouldn't expect so. So we have the coils. Before we do our experiments, though, we have to do kind of basic pre-scan things, such as center frequency and power calibration, which on the proton channel is pretty straightforward. There's an auto pre-scan button, plenty of water in all of us, I hope. So it's easy enough to get signal there and to calibrate, but it's not as easy as it is on proton for carbon, right? And then getting the center frequency correct is crucial for these experiments, right? So we know where the signal is coming from, and we don't have any sort of chemical shift type artifacts. Right, so without much, if any, endogenous carbon, and we don't want to waste any of our hyperpolarized magnetization on a center frequency calibration, what are some thoughts, or what are ways that we can calibrate our center frequency for carbon imaging? Any thoughts? So yeah, the first thing, and what works really well, is just to have an external carbon phantom. So typically we'll have C13 enriched urea, which resonates close to a lot of the metabolites of interest, but does not overlap with them. And we can put these sort of embedded in the coil or around the animal, just within our imaging field of view, so we're able to calibrate the center frequency. So here I've shown some of the results from initial clinical studies where we have the coil embedded, or the phantom embedded in the receive array, and we're able to get very good accuracy in our center frequency calibration. So that works well. Are there any other approaches you could do? Let's say there wasn't room for a carbon phantom, or the metabolites you were interested in overlapped with the urea frequency. What are some other things that we could think of?
Natural carbon in the body?
So you could, so depending on where you're looking at, like some of the endogenous fat can resonate nearby, and it has, if you have bound protons, the T1 can be short enough to get a decent signal. So that's another option. Any other thoughts?
The previous calibration with the phantom in there?
Yeah, so prior experiments, right? You've run an experiment before, and the frequency is at 3213, 5000, right? And so barring drift, that should be more or less reproducible, right? So that's one option. What's one other way you can do it?
There's the proton one.
There you go. So just like on the 14T, right? There's a relationship between sort of the proton Larmor frequency and where the carbon pyruvate frequency should resonate, and that's physics. That's fixed more or less, right? So like Georgios is saying, you can use the water frequency as a surrogate, and then do some math and get your carbon frequency. So there was a nice abstract from ISMRM from the Cambridge group this year, again looking at more the clinical bent, but showing that their prediction, as they say, from the water frequency was more accurate than from either a external phantom, which can be far away and can be obfuscated by field inhomogeneities, or predicted from date, which I think to me is looking at sort of that magnet drift over time. And so looking at the water frequency is a very, I think, clever way to do it, and one that on the 14T is how it's more or less always done.
The same on the
Same on the 3T too, right? So that's pretty standard way of doing your calibration. That gets you pretty close. Shoot.
Why do we use vitamin capsules?
Oh, okay. So you're talking about this. So these aren't for the carbon calibration. I grabbed this from a paper. So you're calling me out here. Good question. This is for on the proton imaging, so we know where the coil is. So the carbon phantom here is for our center frequency and power calibration. The vitamin E capsules are embedded in the coil, so that they show up bright when you do your proton MR. So it's got a limited field of view, so we want to make sure that the coil is where the tumor or the organ of interest actually is. So it helps us. So we've got our frequency calibrated, whether it's from a phantom or from the proton water source. Again, we have the same problem with the RF power. So endogenous carbon signal here, even if we can see a little bit of endogenous fat for frequency calibration, is not going to be enough to do a power type pre-scan. This is really important to get this RF power calibrated correctly, right? We have non-recoverable magnetization, which means that if we play out too high of a flip, we're going to saturate our signal. And it's important for, as we'll talk about in a few slides, this concept of variable flip angle schedules where you're ramping up your flip angles through time. You need that to be accurate when you do your correction and your rate constant calculations. So what are some ways to calibrate that RF power? What can we do? We can use the carbon phantom again, right? That's the easiest way. It's already there. But you could argue that that's a point source, right? And depending on if you have a surface coil or not, that B1 field will vary and can be tough to calibrate. So is there any other way we could potentially do this?
Is this something other than B1 mapping? Is this B1 mapping?
I'm alluding to something like that, but yeah. So you can do it with a carbon phantom, right? By just sort of looking at the spectra and looking for the signal null and then estimating the flip angle, the power from there, right? But if you wanted to get like a B1 map, B1 plus map, how could you do it with hyperpolarized spins where you can't really do double angle approach, and magnitude-based approaches don't really work because of that changing magnetization?
Phase-based approach?
Yeah, so a phase-based approach, exactly, right? And so the most popular one there is this concept of like Bloch-Siegert B1 mapping, which has been around for a few years now. But the idea here is that between your excitation and your readout, you play out a long duration off resonance RF pulse. This RF pulse doesn't excite any spins because it's already off resonance. But what it does do is it does impart phase on the transverse magnetization. That's a function of the applied B1 and the off resonance frequency, right? So you can measure the phase, you know the off resonance frequency, you get a spatially resolved map of your B1 plus or your applied flip angle. So this is oftentimes done as an integrated part of an imaging experiment. So you can maybe use that C13 phantom to get your RF power in the ballpark, and then do a Bloch-Siegert map to either update the power or get a map that you can then use in post-processing to correct for it. Just to highlight what you can do with all these approaches is you can use these sort of so-called RT-Hawk system for autonomous scanning of carbon metabolism. So here it's sort of a one-stop shop to do bolus triggering when the spins arrive, B1 pre-scan calibration, and rapid imaging. So here we have an ROI based on proton anatomy. The pyruvate arrives. Once it gets above a certain threshold, it triggers the scan to do a frequency calibration, so center frequency, and RF power calibration using that Bloch-Siegert phase-based approach. And then with the frequency and power calibrated, it then segues into rapid multi-slice imaging. So if you ever are working on the clinical 3T, this sort of paradigm and approach is one way to make the experience a lot simpler and a lot more robust. Any questions up to this point? Okay. So we've calibrated the frequency, we've calibrated the power. Now we want to actually use that magnetization to encode an image. Okay, and so again, the issue that we have in the hyperpolarized space is that we have non-recoverable magnetization, which we'll keep coming back to. So if you play out a constant tip angle, what that means is it's your signal or your MXY over time is going to be reduced, right? Because our MZ is also changing as a function of time. And so this means that we have unused magnetization after the last excitation or time point. It can also cause some filtering in our images. So if we look at a simple ground truth simulation here, there are, in a Cartesian acquisition, two sort of main ways to acquire data. You have sequential, where you acquire data sort of from top to bottom in K-space. And then you have centric phase encoding, where you go from center of K-space out. So one of those will act as a sort of pseudo low-pass filter, right? Because our MXY is changing over time. And one will act as a pseudo high-pass filter. So based on sort of how I describe sequential and centric phase encoding, which one would act as a high-pass filter? The sequential phase encoding or the centric phase encoding? Does that concept of filtering make sense to you guys? Yeah. So what's a high-pass filter in an image? What's a low-pass filter? Sure, right? So if we have this idea of, let's say, with the constant tip angle, the first few phase encodes will have more magnetization than the last few phase encodes, right? Which of the two approaches, centric or sequential, will act as an effective low-pass filter? Centric, right? Because we're requiring center of K-space first, so we're going to have more blurring. If we do sequential, we're going to go from sort of high spatial frequencies to lower. We're going to have an edge effect. Here's a fun question. From this image here, can you tell me which direction is the frequency and which one's the phase? Or do you not have enough information? Got a 50-50, or I guess 33% chance to get it right. Which way are the artifacts showing? Top down or left right? Yeah, okay, so it's left right, right? That's where the artifacts are. That's the phase encode direction. So here the issue arises because our MZ is changing over time, because we're using up some of that magnetization for each TR with a constant flip angle. So one way around that is to simply use a progressive or variable flip angle schedule that we talked about briefly a few slides before, right? So this idea arises from the fact that we know we're using up some of this magnetization MZ for each TR from our RF pulse. So what we do here is we basically just increase our flip angle through time such that we have constant signal or constant MXY for each phase encode. So here what this does is it gives us constant signal through time, and we account for this lost magnetization or reused magnetization. And because it ends at a 90, we have efficient or complete usage of all of our polarization. And because our signal is constant through time, then we're able to actually recover or recapitulate the image without any low or high pass filtering on top. So one of the other concepts I want to bring in here is that, okay, we can do this variable flip angle schedule through time to give ourselves constant signal. But one thing that we can be cognizant of is that the signal of the injected substrate, which is typically pyruvate, has much higher signal intensity and much higher concentration than that of the metabolites, lactate, alanine, and bicarb. So when you play a constant flip angle for all your metabolites, it typically means you overflip, or you have sort of really high pyruvate SNR, which is good, but it also means you tend to maybe not have as good of SNR as you'd want for lactate. So an alternative approach here is to use this idea of like a variable flip angle through frequency, sometimes called a multiband excitation, where you say, I know I have much more magnetization or concentration of pyruvate than lactate, so I'm going to give it a lower tip angle, which gives me still adequate pyruvate signal through time, but it saves some of that magnetization, giving us more lactate SNR for longer amounts of time, while still giving us good pyruvate. Yeah. So
Can I ask a question about that?
Yeah, sure.
So, with the excitation, is it a volume or a slice? Is it, what I'm trying to understand is, if the pyruvate's coming into the system and you're exciting, like one way I could see doing it is just do a 90 with every excitation, because I'm not going to see that pyruvate again.
Well, yes and no. You might not see that pyruvate directly, right? But what that pyruvate's going to do is it's going to metabolize into lactate and alanine, right? And bicarb. So if you play out a 90, then you're relying strictly on fresh pyruvate coming in, perfusing, and converting to see any signal at later points in time, right? So by doing a lower tip angle, you're basically saying, okay, we're going to have some of that pyruvate, like you're saying, is going to, like in the vasculature, it's going to be in your slice for that time, and then 3 seconds later, it's going to be out. But a lot of it's going to hang around kind of like in that extravascular, extracellular space, in which will slowly be taken up into the cells and then be converted into your metabolites. So here it's simply, I think, recognizing the fact that it's going to see multiple excitations, and because you have a higher concentration, you can afford to give it a lower tip angle, still get adequate image quality. So this is just an example of this concept being used in practice in a preclinical study. So here we do a multiband tip angle. This is taken to the extreme where you don't really see any lactate conversion at all, and pyruvate kind of comes in and comes out. But if you do a more aggressive multiband approach where you go to even lower tip angles and then increase that flip angle through time, you're now able to capture pyruvate kinetics, but also its conversion into lactate. So up to this point, we've talked a little bit about differences in coils and how you do frequency calibration and power calibration and some of the outcomes of different flip angle schemes when we have non-recoverable magnetization. So now that we have all that, we can talk about how we can actually encode and acquire this data. So a one-slide synopsis of K-space. Not much you can say in one slide. But the goal of all these experiments is to turn your NMR signal, into a spatially resolved image. In our case, both spatially and spectrally resolved, And so we can accomplish the spatial encoding by using gradients in X and Y, or X, Y, and Z for 3D to encode our magnetization spatially. But for hyperpolarized substrates, we need to acquire a little more than that, We need to not only acquire our 3 spatial dimensions for 3D volumetric coverage, we want to acquire this data through frequency, so we can separate or resolve pyruvate from, let's say, lactate and bicarb, or bicarb from CO2 in the case of pH imaging. We also want to acquire this data through time, so we can capture the kinetics and extract first-order ray constants. So kind of break down the imaging into 2 different classes. We have the metabolic substrates, like pyruvate, that we oftentimes think about and concern ourselves with. And then we also have these inert substrates, like urea and terbutanol, that are inert, or not metabolically active. So I'll talk about these guys, first. And so here the case is you only have one single resonance present. So urea is HP001, and terbutanol, they're all effectively perfusion type substrates. They're not converted. They're one resonance through time. And so here it's it's a simpler problem. You don't have to concern yourself with that spectral information. So you can really acquire this type of data with any type of imaging approach you want. You can do Cartesian at the cost of scan time, or you can easily do something like a single shot spiral or EPI to minimize your scan time and maximize your coverage. What's rather common to do with these approaches, though, is this idea of balanced steady state free precession, where you have sort of recycled magnetization, or no, you recycle all the gradients within each each TR. And the benefit here is, because a lot of these compounds have relatively long T2 times, is this is a very efficient sequence to recycle the magnetization. And you can get to really high and nice spatial resolutions. Typically with spiral and EPI, you're going to talk about, a few millimeters on a side with a relatively thick slice. But with compounds like C13 urea and even the 15N version, which has 5 to 8 second T2 times, you can really push the resolution to around 1 to 2 millimeters isotropic, giving you a great amount of detail that you wouldn't normally be able to achieve. And so the benefits for these SSFP type approaches is you have really high SNR efficiency because you're recycling that magnetization. And it's most beneficial for compounds with long T2 times, and lets you get the highest spatial resolution. So this idea of 1 millimeter isotropic wouldn't really be tenable or obtainable with other EPI or spiral approaches in the current paradigm. But like any good imaging approach, there are downsides to everything. So if you've had an MRI course before, I'm sure you've heard of the concept of balanced SSFP. And what's the big downside to a steady state sequence? Not Nick. I know you know the answer. Anyone but not. What's the issue with balanced SSFP? It's so good if you have such high SNR efficiency. Even on Proton 2, you get really high SNR. Why isn't it the go-to? What's the catch? Y'all told me you've had MRI courses before. Exactly, banding artifacts, right? So the issue that you have here is that your signal is now a function of flip angle, right? But also now has a little bit of a dependence on frequency, right? So the problem comes when you're in these sort of nulls over here. You have essentially effectively no excitation or no signal, right? So instead of having a nice uniform image, we have delta B0 or field inhomogeneities that cause a range of frequencies, even for a single metabolite or single compound. This can lead to sort of signal modulation in your image. And so that's one of the downsides here, is because of the reduced gradient strength, oftentimes we have to have relatively long TRs, 10, 12, 14 or so milliseconds, which, if not accounted for correctly, can lead to banding type artifacts. And how about if we had, let's say, a metabolically active compound like bicarbon CO2 or like pyruvate and lactate? Could you use an SSFP type approach? You could, I'll tell you that. And if you wanted to do an approach like this where you had, let's say, multiple frequencies, how would you do it? So there are a couple ways. It is more difficult to do a multi-frequency approach with SSFP. There are a couple things you can do. You can employ frequency selective excitation, right? So you play out a somewhat long pulse that's not slice selective, so you only excite one compound, and then between that and a judicious choice of your TR, you can essentially excite the compound you want and not excite off resonance frequencies. Alternatively, you can simplify your spectrum. In this case, you can play out spectral suppression pulses to simplify it to a two frequency system, and then use this frequency selective pulse with SSFP to kind of get a best of both worlds. You can excite one at a time, and you can take advantage of the higher SNR efficiency approach here. But for most of the compounds we're interested in, they have a metabolic component, right? We care, yes, where they go, but also more importantly, what it's converted into. So we need to have spatial and then spectral information to be able to resolve pyruvate from its downstream metabolites. We also want to acquire this data through time so we can quantify that reaction, right? Sort of the effective enzymatic activity. So the issue here is that when you have more than one frequency on board, you have to deal with off resonance, right? And so off resonance leads to artifacts. Yeah. For a simple Cartesian acquisition, this leads to a more of a benign shift. For non-Cartesian like radial or spiral, you tend to have more blurring and distortion that becomes worse as your readout duration becomes longer. So look at the point spread function here. For a Cartesian, it's a simple shift. Something like a spiral approach, you get a really broad point spread function. You're not able to really localize anymore. So there are two major sources of off resonance. One is from B0 and homogeneity. The second is from chemical shift. And that's what we're trying to recover or capture that information. So to do this, we need to employ imaging approaches that can deal with both spatial encoding and spectral information of some kind. And there are two main classes here. There's what I call spectroscopic imaging, like CSI and EPSI, and then frequency-specific approaches, somewhat like the SSFP like we talked about before. So spectroscopic imaging techniques, there are a whole host of approaches that you can employ to acquire your spatial and spectral information, anywhere from a conventional FIT CSI, 2D CSI, to Cartesian EPSI, to the more model-based approaches using rapid EPI or spiral readouts. We'll kind of go through all these real briefly. They all acquire the same thing. They all generate metabolite images that are spatially resolved, but they differ in how they do it and mostly in how fast they do it. So 2D CSI or FIT CSI is just chemical shift imaging, right? And this is the most, I'd say, oldest and most basic of pulse sequences. So what all you're doing here is you're phase encoding on both X and Y, so both axes at once to encode your data. So you have sort of phase encodes on X and Y, and then you turn your A to D converter on and you acquire an FID for each point in K-space. So the benefits of a CSI approach are they give you really the highest possible spectral resolution and spectral bandwidth. So you're able to encode a large range of frequencies, and you're able to encode them with very high spectral resolution, so a small sort of bandwidth per point. But this comes at a significant cost, right? So what's the biggest downside to CSI compared to just a Cartesian type sequence? What's the issue? If you're phase encoding on both axes, right, it means you no longer have that readout for free. So it means your scan time is just quite slow, right? Your total time is your repetition time times number of phase encodes on Y times number of phase encodes on X, which you don't typically have for normal MRI scan, right? So it's RF inefficient, which means you need lots of RF pulses to encode that magnetization. But it's also really slow, right? You know, you need to have a long TR so that you can acquire an FID for each point, right? So let's say your TR is 100 milliseconds and you want to acquire 8x8 matrix, which is pretty coarse when you get down to it, right? So that's 6.4 seconds right there for a single slice. And so while you're able to get really high spectral bandwidth resolution, so for things like C2 pyruvate, or for maybe even hyperpolarized glucose, where you've got a wide range of frequencies and they're going to be close together, this is a good approach. For most things, you can do a bit better. You can take advantage of some things. And that's the idea behind sort of EPSI approaches like spiral CSI or echoplanar spectroscopic imaging. So here, essentially, we acquire this FID by playing these repeated gradients, or the same gradients shifted in time by delta TE. So here it's just a simple Cartesian multi-echo scan. So we're tracing the same phase encode line over and over again to get the spectral information. or here it's with a spiral approach where you have single spiral readouts, but they're shifted in time by delta TE. So remember the relationship between bandwidth and sampling time. 1 over that sample time is your spectral resolution. So the closer they are in time, the larger your bandwidth is.
You play the same spiral?
Typically, I mean, you can also rotate it and do all kinds of other tricks if you want to, but the key there is you're playing it sort of shifted in time. So you're acquiring the sort of KX, KY, KF space. And so if it was a single shot spiral, you could play the same one through time. Or if it was multi-shot, you would have different shots on top of that as well. So the pros here, right, is it's more RF efficient, but also it's much faster than chemical shift imaging, because we now have this, in the case of Cartesian, only one access to phase encode. We're now back to a scan time like we typically would have for a normal acquisition, just TR times number of phase encodes. So from our prior example, our scan time would go from 6.4 seconds to shorter than that, around 800 milliseconds. So now it's a lot more palatable, and you can easily get, you know, multiple slices within a single time point. But what are some potential downsides, or what's the biggest downside with an EPSI type approach? Anyone have any thoughts as to what would potentially be an issue here? So instead of having essentially the ADC tell us what our bandwidth is, what's our bandwidth determined by now? Right. Kind of by how fast we can do either our multi-echo readout, or how close we can put our interleaves together in time. So what that results in is it gives you a much lower, typically, spectral bandwidth. Oftentimes you're dealing with echo spacings on the order of 2 to 4 milliseconds, which gives you a spectral bandwidth of anywhere from 500 to 250 hertz, right? So we're looking at a much narrower range of frequencies, which is sometimes fine, you know, for a sparse spectrum, or for pyruvate and lactate at 3T, you know, 500 hertz is good enough. But for other compounds or higher fields, you're going to need a larger spectral bandwidth to be able to resolve these metabolites. So again, that's the biggest downside or biggest catch here. And the other problem you run into is it, alluding back to the issue with the gradient waveforms and gamma, is that we have this trade-off between spatial resolution and spectral bandwidth, right? If you want to go to a higher resolution, you typically need to go to a higher gradient strength or read out longer. But if you increase your duration of that one of those lobes, it makes your echo spacing larger, which decreases your bandwidth. And so these are all trade-offs you have to kind of be aware of when you're planning and designing your experiment. This is less of an issue on the preclinical systems like the Bruker and the Varian, because they have much higher performance gradient sets. But on like a clinical system where you're limited to about 5 Gauss per centimeter gradient strengths, it does have some issues you have to contend with. So just want to briefly introduce the idea of model-based reconstructions. Some of the work that's been done primarily on the clinical 3T does employ them. The idea here simply is that in our spectra we have basically our hyperpolarized spectra are sparse. That means we know sort of a priori where those frequencies are, and they're relatively well separated. And so what that means is, instead of having to acquire a complete spectrum like you do with EPSI or CSI, you can use so-called model-based approaches to minimize the imaging requirements. It's the same acquisition, but it requires fewer echoes with carefully chosen echo spacings to be able to unfold the data. The benefit here is that with fewer echoes, your scan time is shorter, and you can then use that time savings for increased coverage or increased temporal resolution. The idea, very briefly, basically, is your signal is essentially a sum of the spin densities from your underlying metabolites, and then a known chemical shift based on the delta F between on resonance and then the frequency of interest. And then with the known or ignored field map, it's a linear problem that you can then solve with the least squares approach. So you acquire the data in the same way you do for EPSI or spiral CSI, either with a multi-echo approach or just these readouts shifted in time. But the idea is you can do a simple matrix inversion to get K-space for each frequency, and then just do an FT to get the images that you want. But the big benefit here is that you can sort of use extra information like field maps perhaps, but also just shorten your scan time. There's some citations here if you want to kind of read up further on this. So in the last 5 minutes, I want to talk a little bit about this concept of sort of frequency selected imaging approaches versus spectroscopic imaging approaches. So when we think of RF pulses, they're conventional ones like a sync or a Gaussian type shape are either spectrally or spatially selective, right? If you play out an RF pulse without a gradient, they're spectrally selective or have a spectral response. If you play them with a gradient, you have slice selection, right? And so these types of conventional pulses, sync or Gaussian, can typically be only one or the other, right? So when you play out your RF pulse, in this case it's a time bandwidth for sync, in conjunction with a slice select gradient, you have this sort of spatial and spectral response, right? And the problem you have in this case is when you have multiple resonances present, this type of pulse is not frequency selective, right? So if we have pyruvate here and lactate here, we're going to excite both, but the off resonance compound will be shifted in Z, right? So this sort of chemical shift displacement artifact that you might have heard of before. So we can get around this by using these 2D pulses that we oftentimes refer to as spectral-spatial pulses. And these are 2D selective pulses. They're selective in both frequency and space, hence the name spectral and spatial. To first principle, what we're doing is we play out our sort of conventional RF pulse, Gaussian or sync shape, and we just repeat it through time, and then we add this sort of oscillating gradient on top for spatial selectivity. So the individual subpulses control the spatial response, and then the number of subpulses and their separation controls the spectral selectivity, i.e. sort of the pass bandwidth and the stop bandwidth. And these are an important class of pulses because it allows us to excite one frequency at a time while still having spatial selectivity. So when we contrast the conventional sync pulse to a simple spectral spatial, we see a very different response on this spectral spatial plot, right? So the sync, you have this normal shifted through frequency plot, whereas here we have distinct regions of excitation and then regions where we don't excite. So we're able to, for instance, excite pyruvate and no other metabolites, and then we simply shift this band to excite lactate and then not excite the others, right? So it's slice and frequency selective, and we don't have any type of chemical shift artifact. And it's really easy here to use that variable flip angle scheme like we talked about, because you're exciting them independently. You can choose to excite pyruvate at a very low tip angle, then choose to excite lactate at a higher one, and then you don't even have to worry about exciting alanine or hydrate in this case if we didn't want to actually acquire them. But from looking at these two different pulse shapes and the spectral spatial response, what's the one, or what are some potential downsides or issues you have to be aware of when using a spectral spatial pulse?
Can I answer?
Go for it.
Time of an RF pulse?
Sure. Right. So the one big thing is the pulse duration is very different. This is a millisecond. This is around 18 or so. So your pulse is longer. That's definitely one potential issue when it comes to shorter T2s and T2 star compounds.
If you're off frequency, like if your off resonance is enough, you weren't excited at all.
And that's the biggest problem here, and that's exactly right, because we're only exciting these sort of distinct bands in the frequency domain. So this gets back to the importance of frequency calibration. You know, if we think pyruvate's here, but in actuality it's here, your effective tip angle is more or less zero. So you're not exciting it, you're not going to receive it, and your experiment's going to be kind of failed before it even gets off the ground. So that's the biggest issue with these types of pulses, is you have to be very sure and confident in your center frequency calibration. Otherwise, you're going to have poor or unusable data sets. So in practice, the way it works is you have the spectral spatial module before your rapid imaging readout here in EPI. So we do our frequency calibration. We put our center frequency on pyruvate, say with a 20-degree tip angle for a single slice. This can be extended to multi-slice really easily. And then we simply just shift that frequency, excite lactate with the higher tip. And then if we want bicarb, do the same thing in the other direction. And the benefits here really come down to scan times. We acquire data from 3 frequencies in around 150 to 200 milliseconds, whereas if we were going to do EPSI or CSI, it would take anywhere from 8 to 30 times longer to acquire that same information. So now that we have this RF pulse that can take care of spectral encoding for us, just like with inert substrates, we can really use any type of fast imaging techniques. Commonly, most people will use single shot spirals or echoplanar trajectories, which I'll just show here. You can also do Gray's type approaches, which are a combination of gradient and spin echo. But the idea here is the important thing is the RF pulse takes care of your spectral encoding for you. And because now you only have one excited frequency, we can leverage and use all of the rapid imaging approaches that have been used for a while on the proton side and apply them to our hyperpolarized case. So the benefit
question. So the carbon gets metabolized into different metabolic compounds, but there should be some magnetization transfer between the metabolic compounds as well, right? Do you have any idea how much of the signal transfer is due to magnetization transfer rather than metabolism?
So when you say magnetization transfer, what do you?
Like, I don't really know, but the spins like transfer magnetic momentum without actually the carbon going from one molecule to the other.
You wouldn't, it doesn't really happen in this case. Like you're thinking like mag transfer like on the proton side.
Yeah.
Yeah, you don't have that issue here because you don't really have those, like, that relies on like sort of the free water sort of interacting and coming back to free water and the frequency changes there. Here the carbons that we are dealing with don't undergo that same type of, I guess, chemical process. So we don't have mag transfer in the proton sense. You know, we have it due to chemical conversion, right? The enzymatic reactions sort of facilitate that mag transfer, but you don't have it like you have on the proton side. So I'll just quickly wrap up here. The benefits here is that it's really fast, right? So our scan time now in a single shot approach is just TR times number of slices, because your number of phasing codes is 1 essentially for a multi-echo EPI or a spiral type readout. And that means we can then use that sort of savings in scan time to get an increase in volumetric coverage, right? So we can go from a single slice EPSI to a multi-slice or 3D frequency selective imaging approach without any increase in scan time. So we're able to essentially go from 2D to 3D without any hit to our temporal resolution. And the downside that we talked about is that they are relatively long duration pulses, and they're also very sensitive to off resonance. So if our frequency is set incorrectly, we're not going to get very good, if any, data. So it's already past 2, so I'm going to kind of skip around here. I just want to kind of end up by saying that there are lots of different ways that you can acquire hyperpolarized data. For the most part, they all have pretty similar SNR type efficiencies. This paper here did a nice job of going through simulations and acquiring data preclinically using 2D CSI, which they call fit CSI, Cartesian EPSI, and spiral CSI. And for the most part, you have pretty similar results between them. Again, the point spread functions will be different, but overall, SNR, not too much of a difference. This you can use for reference. So yes, there are plenty of ways to acquire your data. really the right sequence to employ will depend on what substrates you're looking at. You know, acquiring data for C1 pyruvate will be very different from C2 pyruvate, right? And so that's sort of the first thing to understand. And once you know that, you can then choose which imaging approach to work with. And each sequence does have its own strengths and weaknesses. So a couple of good review articles here that I'll highlight that you can look for later if you want to follow up on any of this. And I won't go through it here, but at the end of the slides, I do have a list of what sequences and what approaches are available on each system to give you an idea of what you can do out of the box and what work you might need to do to get those sequences up and running on the system you're interested in. So with that, before we head over to the SpinLab lab demo, are there any outstanding questions from the lecture today or from anything else that we've talked about this afternoon? Excellent question. So SAR is sort of a measure of RF heating or RF deposition, right? So interestingly enough, SAR is nucleus independent, right? So it's a function of gamma and peak B1. So your B1's higher, but your gamma's lower. So it all washes out. So for spectral spatial, it's actually almost never an issue because your pulses are so long, right? You know, you could consider a scenario where if you were doing really advanced or short TR SSFP at high tip angles, SAR could be an issue. Or going to 7T versus 3T, SAR could be an issue. But for the spectral spatial type experiments, it's never really a problem. But good question. Anything else? Okay, great. So we'll take a few minute break and then we'll meet in, what's the room number, Econ?
It's the
yeah. Right by the clinical 3T. So we'll meet there in about 5-10 minutes and we'll have a hands-on demo there. Okay, thanks.